Introduction to Mathematical Statements. Hello, everyone. Welcome to the lecture on Introduction to Mathematical Statements. We're understanding these statements is important because they form the basis for all mathematical reasoning and proofs. Here are objectives. So by the end of this lecture, you should be able to first understand what a mathematical statement is, differentiate between uh, simple and compound mathematical statements, and identify examples of mathematical statements in various contexts, and understand the role of logical connectors in forming complex statements, and be familiar with the concepts of truth value, negation, and quantifiers. What is a mathematical statement? A mathematical statement, also known as a proposition, is a declarative sentence that is either true or false, but not both. This means it must have a clear truth value. For example, 2 plus 2 equals 4 is a mathematical statement because it is a declarative sentence and it is true. On the other hand, the square root of 2 is a rational number, is a mathematical statement that is false. However, not all sentences are mathematical statements. For instance, a question like what is 2 plus 2 is not a statement. It is a question. Similarly, x plus 2 equals 5 is an open sentence because its truth depends on the value of x. So if x is 3, the statement is true. If x is any other number, the statement is false. Types of mathematical statements. So mathematical statements can be classified into two main types: simple statements and compound statements. So simple statements are single declarative sentences. And for an example, 7 is a prime number. It's a single declarative sentence, and it is a straightforward claim with a clear truth value. And compound statements are formed by combining simple statements using logical connectors. So for example, 7 is a prime number and 8 is an even number is a compound statement. It's because we are combining two simple statements with the connector end. Logical connectors. In order to form compound statements, we use logical connectors. The main logical connectors are conjunction, disjunction, negation, implication, biconditional. Conjunction is a compound statement using and is true if both compound statements are true. So for example, 2 is less than 3 and 4 is greater than 1 is true because both 2 is less than 3 and 4 is greater than 1 they are true. Disjunction is a compound statement using or, and it's true if at least one of the component statement is true. For example, 2 is less than 3, or 4 is less than 1 is true because 2 is less than 3 is true, even though 4 is less than 1 is false. Negation inverts the truth value of a statement. So for example, if the statement 2 is less than 3 is true, then its negation is false. And implication is here. So an implication, if A then B is true unless A is true and B is false. So for example, if 2 is less than 3, then 4 is less than 5 is true because 2 is indeed less than 3 and 4 is less than 5. Biconditional. So a biconditional statement, A, if and only if B is true, if both A and B are either true or false. So for example, 2 less than 3 if and only if 4 less than 5 is true because both parts are true. Truth value. So each mathematical statement has a truth value, which indicates whether the statement is true or false. And we use truth tables to show all possible truth values for a given logical expression. So if we are to look at the conjunction A and B, we can build a truth table. So in this table, you can see we have A, column B, and column A and B. And A and B is only true when both A and B are true. And this systematic approach helps us understand the behavior of logical statements under different conditions. Negation. So we looked at negation. Um, Negation is a fundamental concept in logic that changes the truth value of a statement. So if a statement is true, its negation is false. So just to give some more example, say the statement, the sky is blue is true, then the negation, the sky is not blue is false. And if we look at the truth table for negation, we have column for A and column for negation of A. And we can see that the negation of a true statement is false and the negation of a false statement is true. Quantifiers. Quantifiers are used to express properties about sets of elements in a domain. There are two main types of quantifiers. First one is universal quantifier. Second is existential quantifier. Universal quantifier states that a property holds for all elements in a domain. So, for example, for all x in real number, x squared is greater than or equal to 0. And we know that this statement is true because the square of any number is always non-negative. An existential quantifier states that there exists at least one element in the domain for which the property holds. So for example, if this means that there exists an x that is an integer, so that x squared equals 4. And this statement is true because we can find x value that holds true, which is +2 and -2. So here are examples to help you solidify your understanding of mathematical statements. We have simple statement, which we went over. We went over compound statement, and we can create compound statement with conjunction by using and it has to be true if both parts are true. And for compound statement with disjunction, uh, it's in order for this to be true, one of them has to at least be true. So if both of them are false, then this compound statement comes out to be false. And statement with negation, and we have universal quantifier and existential quantifier that we went over. So if we are to have problems, we can have problems that are looking like this and determine if the statements are true or false. And here is another example problem, which is writing the negation of each statement, which essentially you're stating the opposite. Conclusion. So if we are to summarize what we've learned today, mathematical statements are fundamental in mathematics and can be either true or false. And logical connectors such as and, or, not, if, and then, and if and only if are used to form compound statements. Truth values and truth tables help us determine the validity of logical expressions. Uh, Quantifiers such as universal and existential quantifiers are used to express properties about sets of elements. And understanding these concepts is important for understanding mathematics and logic because they form the foundation for constructing proofs and analyzing mathematical arguments. This is it for this lecture. Thank you everyone for listening.